Here, Mr. Bergman, would you like a peanut?
I would love a peanut. I like peanuts. Thank you for sharing with me, Mr.
You're
Sam's.
so very welcome. This is something else that I've learned from my children, that sharing is a nice thing to do.
Sharing is good.
Sharing is caring.
Sharing is caring.
My children also watch a lot of Barney.
Yeah. Oh, is that a Barney thing?
Yeah.
My kids never got into Barney.
Yeah, they're probably a little older.
Yeah.
A little too old.
Sharing. Why are we talking about sharing? Here I'm talking about
covalent bonding is when two atoms share electrons.
So we're sharing electrons, just like sharing peanuts.
Yeah. Here, I have another one for you.
That's empty.
I already ate it.
All right.
Yeah.
All right. Hey, we better talk about covalent bonding so we don't waste our kids' time.
These are good.
I know they are.
Okay.
All right. So we need to define a couple of terms here. All right. The first one is a covalent bond. So a covalent bond is where two or more valence electrons are shared between two atoms.
Uh-huh.
So you shared with me, but it's not exactly the same thing because you actually gave it to me. So it's a share thing where we're both kind of get a piece of it. That'd be kind of weird. And a single bond is when one pair of electrons are shared between two bonds. There's actually double and triple, which we'll talk about later when we do some other things. And folks, what you should do is just copy these down, and then you'll see how they apply a little bit later. So it's the sharing principle. Okay, so here let's talk about what causes them to be attracted to each other. Guess what? It's the same thing we learned about in the last two bondings. Positive things are attracted to negative things. Now, it's not the positive ion, it's actually the nucleus of the one is attracted to the valence electrons of the other, and the nucleus of the other is attracted to the valence electrons of the one.
Okay.
So it's still positive, things attracted to negative. That's what causes the world to get stuck together. Yeah, it's positives attracted to negative. Interesting question. Why does positive things attract negative things? You don't know?
It does.
Because it does is actually the correct answer. Because scientists don't know the answer to that question. Why are positive things attracted to negative things? We don't know.
Fundamental force
But it's a fundamental force of nature. So anyways, but that's something that's just true. We don't exactly know why. You'll win the Nobel Prize if you figure that one out. Okay, so in a covalent bond, here we have two atoms. And they're sharing. So the blue atom here on the right, if you will, the blue valence electrons, he's got 7 valence electrons.
Okay.
And the guy with the red valence electrons, they aren't really colored, but that's just for illustrative purposes. There's a big word. They're sharing these two electrons.
So they each have 8.
So they each have 8. And this actually would be called a single covalent bond because they're sharing one pair. A pair is 2 electrons. Yeah. Were you going to say something? No?
Probably, but I forgot.
Okay. Now, to understand this, we have to understand a few more definitions. Again, this is probably a pause and write down moment here.
Yep.
Okay, but let's just kind of go over it while you're pausing or rewriting down. The electronegativity we call from the atomic theory unit.
Yep, that's the one where my son and I were having the tug of war.
Yes.
Yep.
The attraction of one atom for the electrons of another. Remember, fluorine is the highest. Remember, the smaller they are, the stronger they are. Now, we've got some new terms here. Now, this is important to understand. There's there's a thing called a non-polar covalent bond.
Okay, non-polar, meaning it's not polar.
Now, we'll explain polar in a minute. Okay, the electrons are equally shared between two atoms.
Okay, so they each get them as equal amount.
Right.
Okay.
And there's polar covalent bonds. And that's when they're unequally shared.
Okay, so one of the atoms kind of gets the electrons more often than the other one.
Yeah.
Kind of like when my kids share, they don't really equally share, but they'll sort of like let the other kid touch the toy.
And lastly, a dipole. That's when a bond or molecule has unequal sharing.
All right, so if we have a polar covalent bond, there's unequal sharing, it creates a dipole.
That's correct.
Okay.
All right, to illustrate that, a nonpolar bond is, think of the peanuts that we were sharing. So if we are fighting for the peanuts, and if we are equally strong, Mr. Sams and I are twins. Did you know that? We're twins. I can't pull them away from him, Mr. Sams. He can't pull them away. So they're equally shared.
Right. Non-polar bond.
Non-polar bond.
However,
since Mr. Sams is weaker than me.
What?
I get to be the stronger.
Yeah, whatever.
All right. And so if I pull, guess what? The electrons are closer to me, unequally shared. Okay?
Right. So we're still sharing.
Yeah, I didn't take them.
No.
We're still sharing.
Right. But they're closer to him more of the time. So electrons being negatively charged, if Mr. Bergman has them more of the time than I do, Mr. Bergman is slightly negative, and I am slightly positive.
How did you get to be positive?
Because you're stronger.
That's right. Okay. So hopefully that helps you understand how this works. Now, the way we would draw this from a Lewis dot structure perspective, if I have chlorine, Cl and Cl, chlorine has 7 valence electrons. I'm going to put this one right here. And chlorine, the other chlorine, of course, has 7 valence electrons. Now, based upon their electronegativities, now their electronegativities are right here, right? So here's a table of electronegativities. Turns out that chlorine has an electronegativity of 3.16.
Yeah, both of them have 3.16.
They're the same because 3.16 and 3.16, of course, are the same. So if this is 3.16 and this is 3.16, well, they're twins.
Yeah.
So they're going to share them in the middle. So there is no charge. And they're probably about the same strength, aren't they?
Yeah.
Yours aren't identical.
My twins are not identical. One is definitely stronger than the other one.
You would actually draw this like this. Now, this is, because there is equal sharing, this is called a non-polar bond. Now, on hydrogen, let's do another example. Let's do hydrogen bonded with chlorine. That's hydrochloric acid. Chlorine has 7 valence electrons, and hydrogen just has 1. Now, if we look at its electronegativity, hydrogen is 2.2, and chlorine is 3.16.
Whoa. I thought everybody wanted 8.
Yeah, well, hydrogen's one of those ones he's happy with 2 or 0. 0 equals 8. Remember all that stuff.
So if hydrogen gets 2, it's happy because it only
or
wants
0.
to do it.
In this case, actually, well, he's not
going
to
he's sharing. So he's getting 2.
He's getting 2. So the higher the number, the stronger they are. So chlorine is stronger than hydrogen. And so therefore, the electrons, it would actually be more appropriate to draw it like this. And the hydrogen would be here. And because this side has more electrons, we would put a little, that's a little slightly, sigma actually, negative.
Lowercase delta.
Or delta, pardon me. And this is slightly positive because the electrons are more over on this side than that side. And we usually would draw an arrow through this, like this.
Pointing to the negative side.
Pointing to the negative side. Right. So this is a polar bond.
So we're talking about all these electronegativity differences. How do we know when it's polar and non-polar?
Well, we have a chart, Mr. Sanders.
Oh, a chart.
So you copied on a chart. You may want to print, but this is almost too
It's pretty simple.
Yeah, if you are less than 0.5 difference of electronegativities.
Meaning you subtract the values.
Right.
Okay.
Then it's non-polar.
All right.
If it's between 0.5 and 2.1, and this is sort of an ish number.
Yeah, they're
it's kind of
squishy.
Flexible. And actually, if you get above 2.1, it's
it becomes so polar that then instead of sharing, it takes it. It becomes ionic.
So let's just do some examples.
Let's do that. I'm going to keep eating peanuts.
Let's do
your peanuts, by the way.
NH3. NH3 is known as ammonia. You may have cleaned your house with ammonia. Now, the ammonia, we're actually just look at the N to H bond. So if I find nitrogen and hydrogen, nitrogen here is 3.04. I think we should just round to the nearest tenth. Maybe.
Okay, that's fine. So 3.0?
That's 3.0. So I'm going to just go back and label this as 3.0, and the hydrogen was 2.1, I think. 2.2. So this is 2.2. So if you take a difference between those two,
it's 0.8.
That's going to subtract. You get, of course, 0.8. Well, 0.8, if we go back to our chart, 0.8 is here.
Right there. That's a polar covalent bond.
So this one would be a polar bond. We can say polar just for short.
Sure.
Instead of a polar covalent bond, although that's more correct. Let's do sodium chloride.
All right.
All right. So if we do sodium chloride, and we go back and look at our table of electronegativity, sodium is 0.9, and chlorine we already know.
3.2.
So this is 0.9, and this is 3.2.
Okay.
Now wait a second. The difference, this is, you take the big number minus the smaller number, and what do you get?
2.3.
So the difference here is 2.3. Well, which type is that? 2.3 is,
that's ionic.
It's ionic. You know what? You could have figured that was ionic. How else would you have known that?
It's a metal and a non-metal.
Yeah, so when you do the math on these, metals to non-metals are going to be greater than 2.1 by and large. Or what about if I do iodine? Iodine is I2 or I2.
No, this one you don't even have to do the math. Anything that's bonded to itself is always going to be 0.
Right. So
it's just non-polar.
0, and so this one is non-polar.
How about CH4?
CH4. Well, you're just going to look at the CH bond.
Okay.
The H's connect to the C,
All right, so the carbon-hydrogen
The
bond.
hydrogen we looked up a little bit ago, so that's
2.2.
2.2. So I'm going to have to go look up carbon on my
right.
table. Speaking of that table, guys, you may want to print this table out.
Yeah.
Yeah, probably a good idea. Maybe we'll try and include it in the packet when I think about it. This one's 2.6, it looks like to me. So this is 2.6. So 2.6 minus 2.2 is
0.4.
0.4. And I believe the break point was 0.5.
Yeah, so we're going to call that a non-polar bond.
So
I mean, it's ever so slightly polar because they're different, but they're still close enough that we refer to it as a non-polar
That'd
bond.
be kind of like your twin daughters.
Right.
Playing tug of war. Probably one's
Yeah.
a little bit stronger because they're twins, but one's they're fraternal or whatever.
Right.
Related
Yeah, and they're about the same age, but yeah, one probably
about
slightly stronger.
I would say they are the same.
About did I say about the same age?
Yes,
Yeah.
you did.
Well, they're 2 minutes apart.
There you go. That's pretty
Yeah,
close
makes
enough.
a big difference. Actually, though, the youngest one is stronger.
The younger one, yeah, well, 2 minutes.
2 minutes
makes
younger.
a big difference. Good. Well, that's it, Mr. Sams. I think we understand the whole concept of introduction to
Introduction?
covalent bonds.
Yeah, we're good.
All right, cool.